In this video, we will start with process communication. As I have already discussed with you, that as an application designer, you will write a program, and your programs will be up running on two end systems, which both wants to communicate, and their communication will happen through network infrastructure. When as a designer you have designed the distributed application which is running up on different end systems. So in I think hope you understand this, that whenever the host operating system starts running any program in operating system jargon, that is called process. So when two process are running on the same host operating system, so that is the uh, task of operating system to actually make that communication possible, and they um, do it through inter-process communication that is defined in the operating system. But here the problem is that in the distributed application, your whole program you have divided into two parts. I'm considering the client server architecture here. I'm not touching upon the peer-to-peer architecture, how you will design it. But more or less the concept will remain the same, because they are also in P2P architecture. There is a concept of client and server, but that is not static in nature, that is highly dynamic. So, but we will understand this process communication through client server architecture. So you have a whole program, you have segregated one part of it as a client that is running on one host operating system, another part on a server that is running on different operating system. Maybe their operating system may be completely different. So how then the communication will happen? Then the communication will happen through message exchanges. So one operating system on behalf of that application will make one message and will pass it on to the infrastructure, will dictate the infrastructure to send it all across the network and to provide it to the server which is running up somewhere else. Then that server will pass that application data in terms of that message, will once again that operating system will process the web server application, whatever write backs regarding that message, and then pass it on to the network infrastructure. Network infrastructure will once again provide it to the host operating system. Host operating system will provide it back to the application up running as a process on it. Like the same thing will happen in peer-to-peer, but the point is that there is no segregation, there is no clear division when the same node, when the same host will start acting as a client and server. So, but in any sense, whenever the communication will happen through message exchange. So when you have to, because in client and server architecture, it is very well clear that what is the client process and what is the server process. But in generic term, if you have to define the client process and the server process, and the client process is that which initiates the communication, which will seek certain information, which will seek certain services from the server. And the server process is one which is always run waiting for a client to actually contact it, so that it can serve the client. So in that way, even in peer-to-peer, you can understand that what is client, someone who will initiate the communication. The server is one who will then respond to that initiation. Now we will understand the sockets. And the programming which we will understand is on the name of socket. So socket provides a sort of that application programming interface, APIs, to the application programmer, which they can use for writing their applications. So it's a sort of an interface here in this figure. If you can see, it is the all the protocol stack, starting from the transport layer down to physical layer. So the socket provides a sort of an interface in between the application layer, because the process which you are running is on the application layer. The process is nothing but the same code, either the client code or the server code which you have written, that is running at the application layer. So this is the process. So it's a socket is a sort of an interface which will uh, give you an interface in between the application layer and transport layer. So transport layers are providing certain services to the application layer. Those services, in a while we will understand that what services are being taught by this process running at the application layer from the transport layer. But it requires a sort of an interface. Through that interface, as a designer, you can invoke those operations. So whenever this process or the application process will come in contact with the transport layer, whenever it will pass its message, anything it will pass, it will always pass that message through that socket. Socket is not hardware, it's a logical construct, it's a software construct. We will understand that what is socket later on, but for right now, whenever any process on the application layer at a time on a single host, there may be several applications running. Each application will maintain a socket. So whenever they will pass the information to the transport layer, so socket will act as an interface. So through socket only, that corresponding process will pass that information to the underlying layer, that is the transport layer. Down the transport layer, then the operating system will maintain all those things. So whenever your application is running at the application layer and you have to interact with the transport layer, that interaction will happen only through socket. Each and every application which you will run as a process on the application layer will have its own socket. Only through that socket it will pass the messages to the underlying transport layer. You can take an analogy. When from one home to the next home you have to share any message, so you will pass your information only from your door. So consider that there is an infrastructure running next after your door, which will take care of all the operations, leads to the delivery of your message to the another door. So whenever you have to send a message, you will make a message, you will wrap it up, and then just you will pass it to uh, just you will open your door and you will pass it to next to your door. From there onwards, the job of transport layer comes into picture. The transport layer will pass it on somehow. We don't have to worry as an application designer. We don't have to worry how transport layer will do all these operations. Transport layer will provide that service and finally, eventually deliver it to the door. And that door is once again a socket to the next home. Another person will also open its door and will retrieve that information. So there must be, so I hope you would have understood it through that analogy, that in real world also consider your home door as a socket. So whenever as a user you have to interact with the delivery system, you are only interacting it through that door. So just opening it and closing it. At the receiver, you are opening it and taking all the delivered item, and when you have to deliver it out, you are just keeping it out. You are opening your door and you are keeping it out. That's what exactly the socket is. But it's a logical construct, it's a software construct. Whenever any process will interact with the underlying transport layer, in between comes the socket. Socket has address so as to uniquely identify that, because you have to uniquely identify the process. How you will uniquely identify each process associated with the socket, that's how they are interacting with the transport layer. And whenever you will transfer your message and whenever as a receiver you will receive it only through socket. So as a receiver, whenever you will receive your packet, so definitely there would be a dilemma that this packet is for which socket. So there must be some socket address also, so that the underlying operating system up the layer will only finally eventually deliver it to the right socket, the right. So there must be some identifier which is associated with socket. That all we will see. So this socket provides a sort of an API through which the designer can interact with the underlying transport layer and seek certain services. So what are all those choices as a designer you have? You can have, there are several type of services running on the transport layer. You can choose any one of those services. Like in normal analogy also, there are certain type of post services which you can always seek. You can always seek that the best of the best, or if you want a common service, you can choose a common service. Likewise with the transport layer, the transport facilities are many in number. You can choose any one of, as a application developer, based on your requirement. You can choose uh, those services in the transport layer. Those services in terms of the protocol being provided through TCP protocol or UDP protocol. So you have a choice. In TCP IP protocol stack, you have a choice. Either you can opt for TCP protocol or you can opt for a UDP protocol. They provide whole different bunch of services, all that we will discuss later on. And next, it will provide you some sort of another facility through that API, socket API. You can change certain parameters. At the transport layer, there are certain parameters like what is the buffer size, what is going to be the buffer size, what is the maximum massive size you can make at once your process starts communicating, what will be the maximum size of the packet which you will share with the other end node. So this type of minor changes you can do through these APIs. So this is all about socket. Now we will go for its identification, because uh, once you will start sending and receiving messages, so these process must have an identifier. And we all know that whenever the communication will happen, end-to-end communication, end nodes had their unique IP address for identifying themselves uniquely globally. So globally, you can uniquely identify those nodes through their 32-bit IP address. We are considering only IP version 4 addressing mechanism. So those 32-bit addresses are there. Now the question comes that whenever the process-to-process communication will start happening, whether this 32-bit identifier, which is associated with the end node, is enough to actually distinguish the processes. Then the answer is no, because many processes are running up on the same host, on the same device, which has a single IP address. There are several processes running. So here on my system, I'm running here MS Team, I'm running here Zoom, I'm running here web browser, I'm running several other applications which are using internet facility. So all those applications which are running on my system, and I have only one single IP address. So then you can't demarcate different processes just based on a single IP address. So you require certain more information. What is that more information? That more information is the port number. You require one identifier along with each process, and that we call the port number. So port number is nothing but an identifier associated with each application. So if I'm using HTTP based application, then the HTTP, that port number is 80. If I am using mail application, then the mail application port number is 25. Likewise, each and every application which you will design at the application layer, you have to register for its port number. There is a port number registry organization where whenever you will design any application, you have to register it so that others can't use it. So that globally your application will be unique. So these are the simple examples for port numbers. So and these are static in nature. They're not going to change. If HTTP I'm talking about, the port number is going to be same 80 always. Mail server it is going to be 25. Like FTP, it is I think 22 port numbers. It will use 2021, and there's whole bunch of port numbers assignments. You can always go and check what is the port number concerning any application which is running on your system. So now comes the socket address. Now how you can uniquely identify the port number, all the processes which are running. Every process is interacting with the down layer, transport layer through socket. Now we will assign address to the socket. That is called the socket address. And what address we will assign to the socket? Socket address is nothing but the culmination of both IP address and your port number. So when you will club both, aggregate both IP address and the port number, then that is the socket address for that process. So here, if you can see, this socket, this process is running this socket. If you have to give this socket as an address, whatever be the IP address of this host or server, regarding whatever be the port number associated with this process. If it is a web process, then and like suppose if the address is X and the process port number is Y, then the socket address would be X:Y. That will be the port address. That will be the socket address. Socket address will uniquely identify now, because each and every process port number will be unique. That identifies them uniquely, so that the socket address is self-sufficient in identifying any process running on any system uniquely. Now we will understand the protocols, the application protocols, which you will use as an application designer, what those application protocols actually do. So obviously, as a protocol designer, you have to come up with the type of messages you will exchange. So I'm considering with respect to web services. So you have certain request messages, and the server will then respond with certain response messages. It varies with respect to applications, what applications you are designing. So you can name it accordingly. I am explaining all these things with respect to web services. So there is up running somewhere web server, and there is web client. So web client is nothing but the web browser. So web browser will initially make certain request packets, request messages, will send it across to the web server. Web server will respond it. So what type of message exchanges will happen? So as a protocol designer, your job is that what type of messages will be exchanged? How will you name them? Then comes the syntax, that how will you actually make up those messages? What will be the fields inside those messages? So whenever as a web protocol designer, HTTP protocol designer, you have to think that what will go as a field in the message, request message, what will go in the field as a response message, how will you delineate it, means how much space for individual field will you give so that others can understand it well. Then the third one comes the semantics, that what and every field represents, what and all these fields are representing, what is the meaning associated with the information which we are exchanging with each other. So that is called the message semantics. Then comes the rule that whenever this message being received at this end, how that end node will respond to that message, how that when and how the process send and respond to the messages. These all things are the rule based. So all these thing goes into the design of any protocol, irrespective of the layer at which you will design it. Most of the things will be common. There are certain public domain protocols which allows for interoperability so that everyone can use it. There will be some sort of a standardization. So these are protocols like HTTP, mail transfer protocol. There are a whole bunch of protocols which are public, which are in public domain. Everyone can use it. There is no proprietary over it. But there are certain proprietary protocols also, like Skype is one of those protocols for communication, which is proprietary held by Microsoft. So then we will understand that as an application designer, what exactly our process when will be up on the application layer seek from the transport layer in terms of the services. Because as we have in the layering design concept also, we have understood that the underlying layer will provide certain services to the up layer. So that in that way, what are those services which application layer will seek from the transport layer? First thing is that there are certain applications uh, which can't uh, go for the data losses. They can't means whenever they want to share that information, they're not expecting any data loss. So that kind of a service also they can expect from the transport layer. In that sense, whenever they will pass it on to the transport layer, The onus is on transport layer to provide this kind of services, that whenever any communication will happen from one application to the another application running on different end systems, transport layer will ensure it to the upper application layer that there will be no data loss. It depends on the application. Like if you are designing an application where you want to transmit an audio, so in that way you can tolerate. There are these are called the data loss tolerant applications. You can tolerate some part of a data in between. If you will lose data, you will not bother too much if it is only audio or video transmission. So some part of that glitch you can somehow tolerate. So those are called the data loss tolerant application. Another is like file transfer, email. Whenever you are sending any email, you don't want to lose onto your data. You want to send all part of your data exactly. Like when you did, you will transfer file. In file transfer, you want to do exact transfer. So these are the applications. So based on the requirement, you will seek these kind of services from the transport layer. So the onus is on the transport layer in providing these kind of services to the application layer. The application layer, you will not write a code for ensuring these things. At the transport layer will write a code to ensure all these things. Then comes there certain applications which are time sensitive, like gaming. Whenever you 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 all are playing any distributed game, so at that time you want a sort of a real interaction, real interactive game. There you require relatively low delay because that makes your gaming experience more live and real. So in that situation, application layer, so suppose any game is up running on the application layer, distributed part of it. Other people are also playing. Then at the transport layer, you seek this kind of services that we are running this process, and this process require less delay. So as a designer, you will choose the protocol which will provide that kind of services at the transport layer. Then comes the throughput. There are certain applications which seek more throughput so that they can send more number of bits per second. The throughput is nothing but from one end to the next end, another end, how many bits you can send per second. So if you are running any streaming application, any multimedia application, so you want more throughput. There are certain protocols which doesn't demand more throughput, so those are called elastic applications like email. But there are those applications which are time sensitive. There you require more throughput because there you have to send more bits per second. So like multimedia application, which is time sensitive. But email is not time sensitive. Whenever you will send any email, even after 5 minutes, 10 minutes, it will receive. It should be received intact. So it falls under the data loss. It doesn't want the transport layer to lose data on its behalf. Then comes the security. Sometimes you want whatever you are sending highly encrypted. You want to ensure data integrity. Whatever you are sending, it will not change over a course of transmission. So all these things falls under the security, and the transport layer you can provide these kind of services also to security. Like there is a protocol TLS protocol. Initially, that TLS protocol was secure socket layer SSL protocol. Both these protocols are in between the application layer and transport layer. So when you will club both together, like HTTP protocol and TLS protocol, then the protocol name is HTTPS. What it does, it will take the message from the socket, and so as it is, whatever the process has shared the message through socket, it will take the message, it will encrypt it. Simply, that's what it will do. It will simply encrypt it, and then it will pass it on to the transport layer. Then transport layer will do a whole bunch of other operations, and then it will pass it on to the information to the end node. Once the end node will receive it at the transport layer, then over that, so that SSL or the TLS layer is there, then once again the reverse will happen. It will de-encrypt it and then pass it on through that socket to the concerning process. So that is the additional feature. If you require as a designer the security, then you have to make proper choice. So at the transport layer, which protocol you will use, how will you use it. So these are the transport services. So along with that, there are several other services too. But as a designer, at the application designer, these kind of services you are looking to, and you expect the transport layer to provide depending on your application which you are designing. Some can tolerate data loss, some are time sensitive, some require more bandwidth, they require more throughput, some require security. So based on your own requirement as an application designer, you actually seek and then use the proper protocols at the application layer, at the transport layer. Now these are certain applications, so like file transfer, email, web document, real-time audio, video, stored audio, video, interactive games, instant messaging. Here we will see that what kind of services, all those services we have seen, what kind of services actually as a designer we seek from the transport layer. File transfer, obviously we can't tolerate any data loss. Already we have seen throughput. Yes, obviously throughput is elastic. We don't require more throughput. More throughput we expect, but that is not the constraint. We doesn't require it. So these comes and falls under the elastic bands, and these are not time sensitive. Obviously, these are not time sensitive. Even if it is taking more time, the, the idea is that there shouldn't be any data loss. That is the bottom line. Then the same thing goes with email and web documents. But with real-time audio and video, these are loss tolerant. Any loss will they can tolerate, but they require certain minimum throughput. If that minimum throughput is not being there, then it is not able to uh, run on the application layer. That is the minimum basic requirement, because the encoding happens at the minimum rate. Whenever you will start any audio transmission or video transmission, initially you will start encoding it at a certain rate. At that rate, when you are encoding, obviously minimum to that level, you have to sync it with the throughput. If uh, if at the same rate you are not sending, you are not transmitting your audio or video, then there will be a time lag. Then there is no point of running any video streaming or any video and multimedia application. So it is time sensitive as well. Likewise, stored audio and video, that is a real time streaming. With stored audio and video, it is also loss tolerant. It is also throughput sensitive and time sensitive. But here with few seconds. In real time cases, it is millisecond. With stored, the point is you can buffer it, so you can drag it to few seconds. So time sensitivity. With interactive games, once again, it falls under the same real time audio video. Instant messaging, it is data loss. Obviously, it can't tolerate any data loss. It is also falls under the elastic band, and it depending on whether you want a real-time interaction or not. So it all depends on what type of application. For instance, messaging you are designing. So there you have to take a call whether it will be time sensitive or not. Now, those two services, which those services which the application designer seeks from the transport layer, so being provided through TCP and UDP services. Here we will see that what exactly we are expecting from the transport layer, whether they are delivering onto that expectations or not. So the TCP service will provide reliable data transfer. Reliable data transfer means whatever you are sending, whatever at the process level, at the application layer you are passing your information from socket to the transport layer, it will ensure that without any error, without any data loss, in proper sequence also, the way you will pass it on to the transport layer, it will pass it on to the next application which is running up on next system where you want to deliver it. So that is called the reliable data, reliable transport. So it provides, TCP provides data loss facility, and it will ensure the flow control. flow control means sender won't overwhelm the receiver. So sender and receiver will somehow sync in terms of their sending capacity and receiving capacity. Then congestion control, this TCP service will also provide a congestion control facility. Uh, Whenever both the parties will start thinking that because of their communication, network is in congestion mode, then they will go back. The sender will throttle itself and will not overload the network. But this TCP service will not provide any timing and minimum throughput guarantee and security. If you want to provide these kind of services at the application layer or in between the application layer and transport layer, you have to come up with your own protocol which will ensure these things. Like in security, when you have to provide security, though HTTP will also use the transport layer protocol, TCP protocol, but in between you come up with a protocol that is called the TLS protocol, and then HTTP and TLS means HTTPS, the new protocol name itself comes. So as a designer itself, you have to come up with a solution. TCP is not going to provide you a solution for security. TCP protocol is not going to provide you any solution for timing constraint and minimum throughput constraint. It's not going to provide. If you have to ensure all these things, so as an application designer itself, you have to come up with either your own proprietary protocol or you have to look for any public domain protocol which will facilitate you in providing those services to the users or the applications. So, and it is connection oriented. So initially the TCP protocol will set up a connection with the server, and that connection will go on till the time the communication will be on, and then they will tear down the connection. So there must always be a client server connection intact. They will maintain that connection to state. Whereas UDP protocol is in complete contrast with the TCP protocol. There is no connection oriented concept here. So whatever comes from the socket, so it will just encapsulate it, add certain minimum on information and the transport layer it will require, and pass it on to the IP protocol. Then it will just rely on the unreliable IP protocol, because the IP protocol is unreliable protocol. So whenever you will send message, you're not sure that it will eventually being received at the receiving end or not. So UDP protocol in a way is unreliable protocol. There is no data transfer guarantee between sending and receiving process, and it doesn't provide connection setup phase. So the protocols where uh, uh, you can tolerate data loss, you can use UDP protocol. Where you are time sensitive, where the protocol, where the applications you are designing which are time sensitive, where you want to reduce the time, like real interactive gaming applications or video streaming, real-time video streaming, there also you can use, because there is no connection setup phase. There is no connection setup phase. Uh, so it's this UDP protocol is a sort of an ad hoc protocol. So it isn't going to, obviously when the TCP protocol is not providing any timing, minimum throughput guarantee, security, there is no chance the UDP protocol will provide any information. So in a way, UDP protocol is providing only one basic thing, which is the task of transport layer. It it's add the unique identifier to the process, that is a socket address. So that's all what it will do. UTCP protocol will also do that operation, because these are all the added information in headers they add, because they have to give TCP, the transport layer protocol ensure process to process communication. How they ensure process to process communication? They give identifier to the process. And what is that identifier? That identifier is a socket address. The UDP protocol just provide that socket address, and then rest leave it to the IP protocol, send it. So it's not going to provide anything. When it is not going to provide anything, so obviously it's not going to provide reliable data transfer, it's not going to provide any timing, congestion, throughput guarantee, nothing is going to provide. So in a way, sometime it may be useful, sometime it is not useful. Let's see the protocols where generally people use which protocol, all that. Email protocol at the application layer, if you have to use, obviously you want reliable communication. So you will go for TCP, and the application layer you are using SMTP protocol. If you want to access anyone's terminal remotely, then obviously the protocol you will use here is a telnet application, and underlying protocol is TCP, because there also you want reliability. You don't want to rely on any ad hoc protocol. So WAP, TCP, because reliability, whatever you are sending, you can't tolerate the data loss. And HTTP protocol, file transfer, once again TCP protocol. So wherever there is a constraint with data loss, you can't tolerate the data loss. Eventually, you have to use the underlying transfer protocol, TCP protocol. Streaming multimedia. Here you are using HTTP protocol, RTP protocol. The underlying is depending on what kind of services you you want to give, whether you want to give reliable service or whether you don't want to give reliable service. Based on that, you can choose among these two protocols, TCP protocol and UDP protocol. And there is one more constraint while choosing it: how much is the bandwidth available to you. If the bandwidth available is more than the structured setup in between the source and destination is good enough to sustain with TCP protocol, you will go with TCP protocol because it's the best one between these TCP and UDP protocol. But if the infrastructure is not well and good in place, then you will go for UDP protocol. Likewise, internet telephony, here also you are transmitting audio. So there you can definitely deal with certain data losses. So you will use the UDP protocol. So as a designer, you have to think, you have to come up with a solution that which one will you use. So when you will interact with transport layer to the APIs, so with common that interaction, the socket programming, these are all the choices in your hand, which protocol you can use as a transport layer. With certain tweaks also with the transport layer, that what will be your maximum transmission unit MTU size. So means the complete in layman, what is the complete message size. So once at a time you can send towards the destination, and in certain basic other information you can tweak as an application designer. And as I have already explained, if you are seeking certain services, you want to provide certain services like security, you want to provide certain services like timing constraint, throughput constraint, these are not provided at the transport layer. There is no protocol in the TCP IP protocol stack which ensure these things. So if you have to ensure as a designer to your users that these things will be provided, then somehow you have to tweak either your application layer protocol, or in between you have to send with some of the protocol which are in the public domain for providing these information. So these are all the add-on things which as a designer you have to think on your own terms, on your own account. Then you will actually come up with the whole protocol stack for your user application. That's all from now. In the next lecture, we'll start with the HTTP protocol itself.